Hello everyone, welcome you all to MSP lecture series on interpretative spectroscopy. So we are discussing about UV visible spectroscopy. In my last lecture, I was discussing about the DD transitions and are the conditions. Let's continue knowing more about that. Electronic spectra of transmetal complexes. Here what would happen is essentially electrons are excited from the ground state to one of the excited states. Such electronic transitions require high energy compared to other transitions. So during electronic transition, we also come across low energy vibrational rotational transitions because each electronic level is associated with several vibrations levels, which in turn are associated with or having several rotation levels. So in electronic spectra, such transitions are too close in energy to be resolved into separate absorption bands. The energy required for vibrational rotation excitation is very minimal compared to the energy required for electronic transition from one level to another one. As a result of that one, what happens? They cause broadening of the absorption band in DD spectra, and as a result, the bandwidth observed in DD spectra are in the range of 1000 to 3000 centimeter minus 1. So in a free gaseous metal ion, if you consider, d orbitals are degenerate and hence no DD transitions are observed. But in a complex, degeneracy is lost because of ligand field splitting the orbitals into two or more levels. For example, if you consider octahedral level, we will be having octahedral field, we will be having T2G composite of dxy, dxz and dyz orbitals, which is lower in energy, and then higher energy EG level composite of dx minus y square and dz square levels. But in the tetrahedral, opposite happens. So E will be the ground state in the HOMO level and T2 will be the LUMO level. So the magnitude of this delta O or delta T depends on the nature of the ligands and affect the energy of electronic transitions and hence the frequency of absorption maxima. For example, if you are considering weak field ligands, of course, you can look into spectrochemical series. How we arrived at a position, a given position for a ligand in the spectrochemical series is considering the donor and acceptor properties of the ligands. And if you recall what I taught in advanced transmetal chemistry, that all ligands, whatever we come across, can be simply classified into three categories. One is pure sigma donor ligands, such as water and ammonia, all neutral oxygen donor ligands, and also alkylamines and arylamines. On the other hand, the next one is sigma donor and pi donor ligands, such as halogens. Here what we have is low energy filled sigma orbitals and low energy filled pi orbitals are there. When such ligands interact with the metal, what would happen? Both of them will be donating to the metal and hence the CFSC, the HOMO-LUMO gap, drops relatively compared to what we saw in case of pure sigma donor ligands such as ammonia and water. The third category is sigma donor and pi acceptor ligands. Example, carbon monoxide, phosphines and nitrogen heterocycles and other things. So in this case what happens? They have low energy filled sigma orbitals and high energy empty pi orbitals are there. And in this case, because of the sigma donation and then pi donation back from the metal to the ligand, what happens? The energy gap between HOMO and LUMO increases. As a result, these complexes are more stabilized, and also in case if you want to have a DD transition, it requires very high energy. So that means the magnitude of delta O depends on the nature of the ligand and affect the energy of electronic transition and hence the frequency of absorption maxima. Extent of splitting is related to the ligand position in the spectrochemical series. So the ligand position spectrochemical series is very important in electronic spectroscopy. So here just look into all d orbitals are classified into four categories here. There is some reason behind classifying like this. So first D0 and D10. D0, D10 complexes are usually colorless, not always. Why they are colored? That I will come back soon. And D0 and D10, you cannot anticipate DD transition. But on the other hand, if you look into D1, D4, D6, D9, they have some similarities. In the same way, if you consider D2, D3, D7, D8, they also have some similarities, and D5 is unique. And what are the similarities between D1, D4, D6 and D9? So D1, we have one electron, D4, one less than half-filled electronic configuration, and D6, one more than half-filled electronic configuration, and D9, one less than completely filled electronic configuration. So that means here they have some similarities, and they show very similar spectra when you consider electronic or UV visible spectrometer when we subject those into absorption. On the other hand, if you look into D2, D3, D7, D8, they have similarities because in D2 we have 2 electrons, and D3 we have less than 2 electrons for half-filled electronic configuration, and D7 we have 2 electrons more than half-filled electronic configuration, and D8 we have 2 less than completely filled electronic configuration. So that means again they have similarities, and the spectra look almost identical except for some anomalies here and there, and these compounds are colored, and D5 compounds are little bit pale colored ones, especially when they are tetrahedral compounds, and they are almost colorless when they are octahedral homoleptic complexes having centrosymmetry. We will learn all those things in detail, but now let us look into HgI2. It is brick red color, and here electronic configuration, if you consider mercury, D10 electronic configuration is there, so no DD transition is there, but still it is intensely colored. When you consider potassium permanganate or potassium dichromate, metal exists in their highest possible oxidation states. That means Mn is in +7 state. All electrons have been removed, and it has a D0 electronic configuration, but still KMnO4 is intense purple in color. And similarly, if you look into potassium dichromate, chromium is in +6 state and D0 system, and also intense orange red color. And similarly, if you look into bismuth triiodide, we have D10S2 electronic configuration. It's orange red in color. And if you look into Prussian blue, here we have iron 3 and iron 2 are there. This is also very intense in color. We will see one by one what is the origin of color in these compounds, as you cannot anticipate any DD transition. So iodide has very high polarizability, which results in anionic charge getting easily transferred to the mercury 2+ cation. So this process releases some energy which falls in the visible spectrum. Hence, we can say that compounds like MnO4, HgI2, etc. are colored. That means what we come across is a term called charge transfer transition. When we talk about charge transfer transition, the moment we look into the electronic configuration, we should be able to tell in which direction charge is transferred. For example, if you look into D10, it is metal to ligand charge transfer transition. On the other hand, if you look into KMnO4, it is D0, it is ligand to metal charge transfer transition. And if you look into Prussian blue, here we have iron in 3 state and iron in 2 state. So here it is metal to metal charge transfer transition. So some of these charge transfer transitions are responsible for the appearance of intense color, the respective colors in these compounds. So now we should come back to the selection rules of electronic transitions. So when we were writing microstates, we saw several possible excited states, and then if electrons are promoted to each state from the ground state, then electronic spectra would have been very complicated and elucidation or interpretation would have been very difficult. But however, all these transitions are governed by certain rules that we call it as selection rules for electronic transition. What are those? So electronic transition may be classified as intense or weak according to the magnitude of epsilon maximum that corresponds to allowed or forbidden transitions. That means what are allowed transitions? These transitions have a E maximum value 10⁻⁴ or more, and probability of their occurrence is very high. These are generally due to pi-pi star transitions, allowed transitions. And then example, pi-pi star transition in 1,3-butadiene shows absorption at 217 nanometer, and epsilon has 2900 represents an allowed transition. Then if allowed transition term comes, there should be forbidden transitions. And here if you look into it, n to pi star transition is forbidden. For this transition, E maximum is generally less than 10⁻⁴. For example, if you consider n to pi star transition of saturated aldehydes and ketones, which exhibit a weak absorption of low intensity near 285 nanometer and having a E maximum value less than 100 because they are forbidden transitions. So that means which transitions are forbidden and which transitions are allowed, we can look into it now. Not all theoretically possible electronic transitions are actually observed. That's what I told you, because they are governed by selection rules. Selection rules are there to distinguish between allowed and forbidden transitions, and allowed transitions occur, forbidden do occur, but much less common and are of low intensity in nature. So now the first one is Laporte selection rule. What is Laporte selection rule? The transition should involve delta L equals plus or minus 1. If that is involved, they are called Laporte allowed and have high absorbance. That means during electronic transition, azimuthal quantum number should change. It should not be, delta L should not be 0. This is about Laporte selection rule. And then what is spin selection rule? During the electronic transition, electron does not change its spin. This electron is getting excited to the higher level, it should stay something like this. This is allowed, and then if this electron, if it goes like this, this is not allowed. So that means what it says is delta S equals 0. That means during electronic transition, electron does not change its spin. If the upward spin is there, it should go and sit in excited level, something like that. It's not allowed to go and sit like this. This is exactly opposite to NMR selection rule, where in order to see nuclear spin transition, flipping of nucleus, when you are applying radio frequency in a direction perpendicular to the applied magnetic field, the frequency of that one matches the present frequency of the nucleus. Then what happens? It will start wobbling and coming out from more and more coming out of the axis of magnetic field, and it flips. So there, if you consider in NMR, delta S equals plus or minus 1. One should remember, whereas in case of electronic transition, it is delta S equals 0. In nuclear transition, it's opposite. Upward spin will become downward spin. So here, the spin state doesn't change. That means DD transitions are strictly speaking Laporte forbidden. That means we should not anticipate any DD transition at all, because it says delta L equals 0. And all d orbitals have the same delta L value. And of course, since they are Laporte forbidden, that can be seen from the epsilon value. Molar absorptive coefficient will be in the range of 5 to 10 liters per mole per centimeter minus. When transition metal forms a complex, then why do we observe DD transition? When transition metal forms a complex, M is surrounded by ligands. Mixing of d and p orbitals may occur, and as a result, transitions are no longer DD in nature. Of course, you can also recollect from valence bond theory about hybridization. In case of octahedral complexes, when octahedral compound is formed, the hybridization we are giving is D2sp3 or sp3d2. So that means S and 3p and 2 d orbitals, dz square and dx minus y square, will combine to generate a set of 6 hybrid orbitals, which are having the properties of all the ligands which are involved in this hybridization. So as a result, what would happen? The d orbitals present in sp3d2 are no longer d orbitals we observed in free gaseous metal ion. So that means mixing of d p orbitals may occur. As a result, transitions are no longer, when that is split into T2g and EG, they are no longer d orbitals of same property that we saw when it is not kept in the ligand field. So now, because of the mixing, they lose original, so D character. As a result, what happens? It becomes Laporte allowed, and hence we see DD transition. So because of slight relaxation in Laporte rule, DD transitions are observed. Mixing is common when complexes lack center of symmetry. Mixing is even more pronounced when they lack center of symmetry. So now let's look into tetrabromomanganate 2 minus. This is tetrahedral. So manganese in +2 state, and it's a D5 system. And then if you look into pentamine chlorocobalt 2 plus, is octahedral with unsymmetrical substitution, and both the compounds are colored. This compound is also colored, this compound is also colored. So in case of MnBr4 2 minus, if you consider it is a tetrahedral compound, we have something like this. So here if you see D5 system, all the electrons have spin like this, and here if we promote one of this electron, it should go here or here or here. If it goes here, both the electrons will be having the upward spin, and that is not allowed. That is the reason this is spin forbidden transition. But nevertheless, in tetrahedral compounds, that is allowed, and you can see they show color because they lack center of symmetry. And same thing is true in case of this one. We have D7 here. So here any of these electrons with downward spin can go and transition can be seen. So, and here also it does not have center of symmetry, its unsymmetrical substitution is there, these compounds are colored. But on the other hand, if you look into homoleptic compounds such as hexamine cobalt 3 plus or hexamine copper 2 plus, they have center of symmetry, though mixing of p and d orbitals are observed, and they, as a result, they are not colored or very pale colored in nature. So then why this color comes despite they having center of symmetry? That means when the metal to ligand bond vibrates, so that the ligand spends an appreciable amount of time out of their centrosymmetric equilibrium position. As a result, small amount of mixing do occur and low intensity transitions are observed. So that means when they are vibrating with respect to the mean position, it so happens that all the ligands will be at a different position from the central metal atom. As a result, they come out of centrosymmetric equilibrium, and hence this is essentially due to the mixing of p and d orbitals, and that results in low intensity transitions. So now you can see the type of transition. Spin forbidden transitions will be having very less epsilon value, typically less than 1, and the example is hexaaqua manganese 2 plus. It's a homoleptic compound having center of symmetry, and again having d5 electronic configuration. This is spin forbidden and also Laporte forbidden, that is. And if you consider Laporte forbidden and spin allowed, they will be having epsilon value anywhere between 1 to 10 and then R 10 to 1000. For example, if you look into hexaaqua titanium 3 plus, a D1 system here. So here center of symmetry is there, octahedral compounds homoleptic, that is the reason this value is low. And then if you look into tetrachloronickelate 2 minus, this is a tetrahedral compound, center of symmetry is not there, and then it is a spin allowed, and here the value is about 10 to 1000. Okay, so it's slightly better. And in case of charge transfer, we can see 1000 to 50,000, for example, manganate ion, potassium permanganate. This is essentially ligand to metal charge transfer transition. Okay, so now let us look into the system and type of spectra we will see, and also when they are allowed, Laporte and spin allowed. So when a transition is Laporte allowed and spin allowed, that has to be charge transfer transition, and they will be having very high epsilon values. Example, TiCl6 2 minus, and then a partly allowed and some PD mixing is there. We will see DD transition. Here it is 500, and for example, if you take tetrahedral compounds of bromo and chloro, so tetrabromo cobaltate or tetrachlorocobaltate. And then Laporte forbidden and spin allowed, we have quite a few. Here it is again termed as DD transition. Epsilon value is in the 10 to rise to 10, where we have center of symmetry is there. For example, hexaaqua titanium 3 plus or hexaaqua vanadium 3 plus here. Then partly Laporte allowed and spin forbidden are those where we have typical D5 system. D5 system, epsilon value is very low, 4 here. And if it is spin forbidden and Laporte forbidden, the value is very, very minimum 0.02 epsilon value. In those DD transitions, very weak and very weak intense in nature, intensity is very, very weak, and these are especially having D5 system having center of symmetry. An example is hexaaqua manganese 2 plus. Then let us look into what are the factors that affect crystal field stabilization energy and absorption wavelength. So the absorption wavelength is directly proportional to the crystal field stabilization energy we see, and that is governed by spectrochemical series. I have given here a very extended spectrochemical series here. Most of the ligands I have included here. The magnitude of delta depends on the charge on metal, whether it's metal in +1 state, +2 state or +3 state, and also it depends on position in periodic table. That means whether it's a 3D series, 4D series or 5D series, and also the ligand field strength. All these three factors have an influence on the magnitude of crystal field stabilization energy, and here increasing with increasing field strength, so wavelength decreases. So that means as crystal field stabilization energy increases and HOMO-LUMO gap increases, as a result what happens? High energy is required, wavelength decreases. for those things. And you can see here, in case of octahedral, the energy gap between HOMO and LOMO is very high, and that is slightly less in case of tetrahedral. And here in case of square planar, we are considering this transition here, dz square to dxy level. So now let us consider metal to ligand charge transfer transition. If the metal is in a low oxidation state, that means it is electron rich, and the ligand possesses low lying empty orbitals. They should have pi star in case of aromatic ligands, or carbon monoxide, or N-heterocyclic carbene, or sigma star in case of phosphines. Then a metal to ligand charge transfer transition occurs. We should remember here, metal is in low oxidation state. When the metal is in low oxidation state, it has more electrons. It is almost vulnerable for oxidation. That means it can readily give electrons. So those metals, when they are combined with ligands having low lying empty orbitals like pi star or sigma star, then a metal to ligand charge transfer is smooth, and you can see MLCT here. MLCT transitions are common for coordination compounds having pi acceptor ligands. Whatever the back donation, we call it metal to ligand back donation. It is nothing but metal to ligand charge transfer. Upon the absorption of light, electrons in the metal orbitals are excited to the ligand pi star orbitals. So metal pi orbitals like dxy, dyz and dxz combine with pi star to generate a set of molecular orbitals, bonding and anti-bonding, and this bonding will be occupying the electrons taken from the metal. This we call it as metal to ligand charge transfer or metal to ligand back bonding. So metal to ligand charge transfer transitions result in intense bands. Example, if you consider tris 2,2- bipyridyl ruthenium 2+, this orange colored complex is being studied as the excited state resulting from this charge transfer, which has a lifetime of microseconds, and the complex is a versatile photochemical redox reagent. So other examples are tetracarbonyl phenanthroline tungsten and also 2,2- bipyridyl tricarbonyl iron compounds. Several examples you can find which exhibit metal to ligand charge transfer transition. So let us learn more about charge transfer transitions in my next lecture. Until then, have an excellent time. Thank you.